Hey students, how are you doing today? Mr. Elliott forgot to bring his hat to school, so you're gonna have to deal with bad hair Elliott. Let's make Elliott small very quickly. And Elliott's gonna be very small today. And anyway, today's lesson. This is the part one of a five-part lesson. One of the key points of this semester is this lesson. First part of this lesson, this is all under the umbrella of graphing transformations, and today we're going to be doing translations, which is the first of the transformations, and we're going to be applying this to the quadratic family. We're going to have a lot of parent functions this particular year, and each parent function we usually refer to as a family. So our first parent function is the quadratic. If you've the parent function is y equals x squared, and if you just did a quick graph of it, or if you already know what this graph looks like, it looks like I think of it as thinking like the letter U. There are 5 key points I'd like for you to graph whenever you're graphing a quadratic family graph, and that would be these points. Your graph, of course, passes through 0, 0. It passes through 1, 1. If you plug 2 into it, 2 squared is 4. If I plug negative 1 into this, negative 1 times negative 1 is positive 1. Negative 2 times negative 2 is positive 4. And if you went ahead and graphed these points, you'd have them like this. You connect the dots. Oops. And that is our first parent function, y equals x squared. Now, you're going to hear me a lot over the next several days and weeks refer to being on team graph paper or team non-graph paper. There are kind of 2 different ways of doing these graphs, and one of these ways does not involve graph paper, and one of these ways must involve graph paper. It's important for you to decide over the next day and weeks to decide whether you want to be doing these problems entirely in graph paper or entirely not in graph paper. During these lessons, I will solve problems both ways. Then it's ultimately up to you to decide which way you feel more comfortable with. So that's the quadratic formula, quadratic family. Anytime you graph any kind of x squared graph, your graph shouldn't, for all intents and purposes, look just like this shape here. Maybe it'll be pointing up, maybe it'll be pointing down, maybe it'll be the left, right, up, down, maybe it'll be stretched, maybe it'll have a different look to it, but in the end of the day, it should look like this general U-like shape. Okay. Next, I'd like to get into actually doing some translations. And for this next part, you are going to want some graph paper. Part 2, translations. Specifically, we're going to take this graph of y equals x squared and do a couple different things to it. First graph I'd like to do is y equals x squared plus 3. And I already made a table of values for it. Going old school here. So if I plug negative 3 into this equation, negative 3 squared is positive 9, plus 3 is 12. Negative 2 squared is 4, plus 3 is 7. I think I've made a mistake. No, I haven't. Negative 1 squared is 1, plus 3 is 4. If I plug in 0, 0 squared plus 3 is 3. If I plug in 1, 1 squared plus 3 is 4, 2 squared plus 3 is 7, 3 squared plus 3 is 12. And if you graph this graph then, I'm using graph paper for this graph, I had 0, 3, 1, 4, and negative 1, 4, 2, 7, and negative 2, 7. And I think that's actually enough information. While that 3 information is helpful, I have the 5 points of importance that I talked about in my very first problem with the parent graph. anyway, I have a graph that looks like this. And if you compare this graph to y equals x squared, our original graph, the two graphs look basically the same. The only thing that happened is that this graph got shifted up 3. So all of these y values moved up a value of 3. Okay. What if I tried y equals x plus 3 in parentheses quantities squared? And for this time, I'm going to graph it in between -6 and 0. And I'm kind of doing that because I'm the teacher and I have inside information about this problem. Well, if I plug -6 into this, -6 plus 3 is -3. If I square -3, that's +9. If I plug -5 into the equation, -5 plus 3 is -2. -2 squared is 4. If I plug in 1, or -4, out it's going to pop 1. -3, -3 plus 3 is 0. You square 0, you'll get 0. And as you plug in these numbers, you would end up with these all these different values. And if you graphed them, let's graph this now. I have -3, 0, -2, 1, -1, 4. Uh-oh, I've made a mistake. -2, 1, -1, 4 up here, like there. And then -4, 1, -5, 4, and -6, 9. I'm not going to graph that last 9th point, but the whole point of this is this graph, same thing, just as my original point, my original graph, this looks just like this original quadratic family graph, but this time what I'm noticing, the difference between these two graphs is this graph has moved to the left 3. So going back, this graph was going up 3, and this graph was going left 3. There's got to be a faster way to do this, right, everybody? There has got to be a faster way than graphing all these equations by hand, and there is. I want to do a lot more translations, but I want to look at all these translations quickly. So let's take a look at this. Number 1, I'm just going to graph y equals plain old, oops, I should start over, include the y. I'm going to graph y equals x squared. Number 2, I'm going to graph this y equals x squared plus 3. Number 3, I'm going to graph y equals x squared plus, 7. Number 4, I'm going to go y equals x squared minus 4. And I'm going to use this piece of technology that I have available to me. It's a website. It's called Desmos.com. And if you want to pause this video for a minute and go and check out this website, see how it works, I recommend it. I have this little graph right here. All right, so this is Desmos.com. And let me show you how it works. You start off with something like this, and you go to this box here, and you just type in your first equation. So my first equation I was going to graph, if we go back and look at it, got to make this small again. I'm going to graph these 4 equations. I'm going to graph y equals x squared plus 3, y equals x squared plus 7, y equals x squared minus 4. You should do this with me as I'm doing it. Expand your learning. Y equals, type in x, and then down here at the bottom, right here is the squared button. So you just type that in. Hey, there's a y equals x squared, just like our original graph. Then I hit enter, and I can print up, immediately bring up a second one. Y equals x squared, hit the squared button, plus 3. Whoa, that's so much faster than doing it by hand. All right, so that's the blue graph. Third one, y equals x squared plus 7. So I'm noticing all these vertical shifts. And then finally, y equals x squared minus 4. And that graph's down there. So let's take a look at these 4 graphs together. Y equals x squared had the center point. X squared plus 3 was the entire graph, but shifted up 3. y equals x squared plus 7, the entire graph shifted up 7, and y equals x squared minus 4, the entire graph shifted down 4. So, so going back to our problem here, if we graph these three graphs, y equals x squared is the normal graph. This graph went up 3. This graph went up 7. This graph went down 4. So it appears that if you're adding a number or subtracting a number to the function, your graph is going to be going up or down according to whether you are adding or subtracting to that equation. Interesting. At least I think it's interesting. All right, let's do 4 more of these, but this time let's compare y equals x squared. Y equals, and then let's have it be like this one that we graphed earlier. X plus 3 quantity squared. I keep the same type of theme. I'm going to go with x plus 7 quantity squared and x minus 4 quantity squared. So same thing. We're going to be doing some adding and subtracting, but this time the adding and subtracting is going to be inside the function. Oops, change this. So it's going to affect this graph. So I'm going to just get rid of all this. And then I'm going to go into this x, erase that, and put in x plus 3. X plus 3. And then close the parentheses, then the squared's on the outside. Interesting, the graph said plus 3, but it went 3 to the left. This next one, I typed it in, we have x plus 7, close parentheses, squared. That graph went 7 to the left. This one, this last one, we wanted to go with x minus 4 quantity squared. That one went 4 to the right. Interesting. So let's make this smaller or bigger, depending on what you need. So this is what I'm noticing. That x plus 3 squared, this one went left 3. X plus 7 quantity squared went left 7. This x minus 4 quantity squared, that went right 4. So what you're seeing here is something I'm going to refer to is this a common theme, that when you are doing something outside the function, all right, let me make this, let's make the Desmos smaller. Thanks, Desmos. You did an awesome job today. You should use Desmos, everybody. It is a good tool. So I found interesting that when we were adding numbers outside of the function, it was controlling it up or down. And at the same time, it's kind of doing what common sense would tell you. When you're thinking up and you're thinking addition, addition means up. Addition means up. Subtraction means down. And it's all outside of the function. Whereas this other one, when I think when I'm thinking right and left, but I'm thinking adding, that makes me think to the right. Adding to the right, adding to the right, subtraction to the left. But what actually happened to the transformation was the exact opposite of it. The x plus 3 went left 3. The x plus 7 went left 7. The x minus 4 went right 4. So inside the function, controlled it left and right. And it was kind of opposite thinking. Oh, that's a confusing point. That when we added, it was going left. When it was subtracting, it was going right. Outside the function, Outside the function controls whether it's going up or down. And up is the addition, down is the subtraction, and it's not opposite thinking. It's exactly what common sense tells us. And this is it's an important point, but it's also kind of confusing. So I want to do some examples next. And my first examples involve a graph, and this is just doing plain old translations. And let's say that they give me some f of x graph that looks like this, and the key 3 points are negative 2, 0, 2, 0, and 0, 3. And they have this graph being labeled as f of x. Okay. The instructions are to graph, number 1, y equals f of x plus 3. All right, as I said earlier, outside the function, this means you're either going to be going up or down, and you do it's not opposite thinking, you do exactly what they tell you to. So in this case, it's saying plus 3, so it's outside the function. I do exactly what it tells me to, so I take this entire function and I graph it up 3. I know that this graph is essentially going to look exactly the same. The only difference is that if this coordinate went up 3, it would go up 3 to negative 2, 3. This coordinate would be 2, 3, and this coordinate would be 0, 6. So I took that graph, I sent it up 3. Example number 2. What if it said y equals f of x minus 4? Well, this is inside the function. It is inside the function of x. And when it's inside the function, this is when you do opposite thinking. So I see minus 4, so that makes me think subtract 4. That usually means you're going to the left. But no, you got to do the opposite thinking. You want to ask, when is this equal to 0? And it's equal to 0 when x equals positive 4. So it's actually traveling to the right. Right, a distance of 4. So that graph, original f of x, as a reminder, it's up at the top. And I know that this graph is going to essentially look the same, but the coordinates are all going to be right 4. So if I moved right 4 from negative 2, 0, I would actually be at 2, 0. If you went 2, 0 and you traveled to the right 4, you'd be at 6, 0. Then this point up top, if you were at 0, 3, and you traveled 4 to the right, you'd be at 4, 3. An example 3 where you do both of these together. Let's say that you had to graph y equals f of x plus 1 minus 4. Okay, well, we have outside the function is this minus 4. When you're outside the function, that's going to control up or down. And it is going minus 4, so it's going to go down 4. We are not using opposite thinking, so down 4. And the x plus 1, that is inside the function. You're thinking opposite thinking. I like to think, when is this function equal to 0? This function would be equal to 0 at negative 1. So that means this entire graph is going left, a distance of 1. It's not going to change the way that the graph looks. It's going to have the exact same look. But if you are at the coordinate negative 2, 0, and you went left 1, you'd put a negative 3. Then if you went down 4, that would put you at negative 4. From 2, 0, if you went left 1 that'd give you an x coordinate of 1. If you went down 4, it would become minus 4. Up here at the top, the 0, 3. If you went left 1 from the 0, it would be at negative 1. And then if you went down 4 from positive 3, it would be at negative 1. Another way that you could look at it would be coordinate analysis. We had this xy coordinate, and it went left 1, so we took all the x coordinates and we subtracted 1. It went down 4, so we took all the y coordinates and subtracted 4. Let's try out one more problem from this set, example 4, and it'll be another multi-step one. Let's say that, I'm just going to move this around. This is your original f of x graph, and suppose you had to graph 3 plus, start over, y equals 3 plus f of x minus 2. Well, this 3 plus the function, this is outside the function, so you do exactly what it tells you to. So you're going up 3. This is inside the function, that's going to go left or right, but you need to ask yourself, when is this equal to 0? It's equal to 0 when x equals 2, positive 2. So we're going to go right 2. If you thought about it coordinate analysis-wise, xy, if you're taking all of your x coordinates and you're adding 2 to it, it's going to be x plus 2. If you took all your y coordinates and you went up 3, you're going to be adding 3 to it. So I know that this graph is going to look exactly the same as it always did with these 3 key points. And then these 3 key points, I have negative 2, 0. And if I add 2 to the x coordinate, it would become 0. The y coordinate would become 3. The point 2, 0 would become 4, 3. And the point 0, 3, if I add 2, becomes a 2. If I add 3, becomes a 6. Then I could just go and manually put in all these coordinates. So I have 0, 3. The negative 2, 0 became 0, 3. The 2, 0 became 4, 3. And the 0, 3 became 2, 6. Okay, so that is how you go about graphing functions if you were just, if you're told to do a translation on it. I've gotten 22 minutes into this lesson, and I got some students about to file in. I do want to quickly show one more type of problem, though. For this one, instead of them, having to do the graph, you're going to get the equation. You're going to be given the graph, and you have to write the equation. And I'm only going to show 2 examples because, like I said, I'm running really short on time. Let's say that you had a parabola that looked like this. And today you really only need to focus on the vertex point. Say it had the vertex point 3, 5. Well, you know that a typical x squared graph starts at 0, 0. So to get from the 0, 0 to the point 3, 5, it went right 3 and up 5. And as we mentioned before, if you're going up or down, this is happening outside the function. So outside the function, you've got this plus 5. Left or right is inside the function. And because it's right 3, that means it would be x minus 3. Meaning, if you plug 3 into this equation, out popped 0. And then the inside of the function squared, so it's x minus 3 quantity squared plus 5. Let me do one more example. Guys, anything that you say, the mic's going to pick up, so I need you to be quiet for just one more minute, please. Thank you. Happy Tuesday. Last example, let's say that I had one that this vertex point is at -8, -1. The graph might not be realistic, but this works. All right, normal parent function starts at 0, 0. So to get from this point to this new vertex point, it's going left 8, down 1. So with the left or right, it's going left 8. Think about negative 8. If I plug negative 8 into, you guys, please be quiet for one more minute. If I plug negative 8 into this equation, I want this bracket part or this parentheses part to be 0. So I'd go with x plus 8. Common sense says minus. That's why we put plus. It's on the inside of the function. And that'd be squared. Outside of the function, we're going down 1. So outside of it, we just merely subtract 1. And that is that's writing some equations when you're given a graph. So class is starting right now, so I need to get moving. So I'm sorry that you had to witness No Hat Elliott, and I'll talk to you later. Bye.